Good afternoon, the committee members. I'm very happy to be here to present my PhD dissertation on training algorithms of local support vector regression for dealing with large datasets. First of all, I would like to introduce to you the very general context of the research, and then I will focus on SVR and our proposed training algorithm of local support vector regression for dealing with large datasets. I will terminate by some numerical test results before conclusions and future work. SVM is one of the most popular machine learning algorithms. This is the reason why our research pays attention to SVM. SVM algorithm proposed by Wapnick in 1975 are most accurate models in classification, regression, and novelty detection. They are successfully applied into many domains of application, including face identification, handwriting recognition, text categorization, and bioinformatics. The training task requires the quadratic programming solution, so it has high cost when dealing with large datasets. Although the complexity of SVM training algorithm at least OM square, so it is impractical for large datasets. Many researchers try to improve the training task of SVM, including C-Flat, Shilin, L. Bottu, V. Franks, Magasarian, Tiendo, and Segata, and so on. For this research, we propose the training algorithm called Chaos-VR, KRS-VR, TS-VR, and TS-VR of local support vector regression for dealing with large datasets. The local VR algorithm perform the training task via two main steps. The first one is to partition the large dataset into k-subsets, and follow it. The second one is to parallel training local SVR model on multi-core computers. Each local SVR model is learned from each subset. So our local SVR algorithms are faster than the standard SVR for large datasets, and while maintaining the high prediction correctness. We start from SVM. Let's consider a binary classification task between two classes, +1 and -1. There are many ways possible to separate this data, but what is the best? The best plan is found by two parallel supporting planes, and the first one is for class +1 and the second one is for class -1. The optimal plan is the middle way. The margin is the distance between two supporting planes. Intuitively, the largest margin is the safest model. Any point on wrong side is considered as the error. SVM will simultaneously maximize margin and minimizing the error. This is accomplished throughout a quadratic programming. The classification of new data point X is based on the size of Wx minus B. The training task of SVM uh, require a square solution. Therefore, it's a high cost when dealing with large datasets. For maximizing margin and minimizing errors, it exists Lagrangian dual of one. Variations on SVM algorithms yield different classification functions. No algorithmic changes are required from the usual kernel functions, a linear product, other than the modification of the kernel function evaluation. We can get different of SVM models. For support vector regressions, for dealing with the regression task, SVR algorithm tries to find a hyperplane that has at least a small epsilon deviation from the target value y. An intuitive geometric approach illustrates that the regression task of the SVR is considered as a classification problem of SVM. The positive class D plus is formed by increasing the target value y by epsilon. The negative class D minus is formed by decreasing the target value y by epsilon. The optimal plane found by SVM approach for separating D plus from D minus is identical to the solution of the SVR approach. SVR shows how to learn accurate model for regression. SVR deals with nonlinear by substituting kernel functions. SVR learning requires quadratic programming where we obtain the global optimum, but the algorithmic complexity is at least OM squared, making SVM impractical for large datasets. And I would like to focus deeply in our research about training algorithms of local support vector regression for dealing with large datasets, and we will introduce four local SVR algorithms, that is KSVR, TSVR, KRSVR, and RTSVR. KSVR uses the K-mean algorithm to partition the full training dataset into K-clusters or subsets and train local SVR models in the parallel way. We can see three local spheres on the right part versus the global sphere on the left part. And the algorithm number 2 is TSVR. TLOCAL-SVR for large datasets uses the decision tree algorithm to partition the full training dataset into K-terminal nodes or subsets and train local support vector regression models in the parallel way. We can see here is a global SVR versus or local SVR on the right part. Performance analysis of KSVR and TSVR. For algorithmic complexity, our local SVR improve KP time training speed against the standard SVR algorithm. For generalization capacity, we turn back to the theorem 5.2 of Wapnick, and we can see the maximum margin hyperplane found by minimization of R square divided delta can generalize well. The generalization ability of large margin hyperplane is high. With the theorem 1 and theorem 2 of Dou. So, based on the three theorems, we consider the generalization capacity of local SVR. Probability of error is bounded by 1 divided mk rk square divided delta k. And with the theorem of Dou, the theorem 1 and 2, we have delta xk. It means the margin of the local local SVR always greater than or equal the margin of the global SVR. The subset xk is always contained in X. So RK is less than or minus or equal R, and MK is always less than or equal M. Therefore, is existing a compromise between the locality subset and the generalized ability, the margin size. Due to the subset Sk in the full training set X, Rk less than or equal R, but the margin size of local SVR delta k is greater than or equal the margin size of the global one. So in this case, we consider the parameter k in KSVR and TSVR. This k is very important to control the generalization capacity and the computational cost. If k is large, then local SVR reduces significant training time but making a very low capacity. If K is small, then local SVR cannot improve training time, but giving a very high capacity, K is setting so that the subset size is large enough, for example, 200 individuals. I would like to mention about the algorithm number 3. It's training algorithm KR, SVR. It's T, we call T random KSVRs. The training algorithm KR-SVR learns T random KSVR models to improve the generalization ability of KSVR alone. The KSVR algorithm trains the T-KSVR model from the T bootstrap sample, sampling with replacement from the original dataset using an apostrophe dimensions randomly sampling without replacement from an original dimensions. For the algorithm number 4, the training algorithm RT-SVR. T-random T-SVR is the RT-SVR algorithm trains the ensemble of T-random T-SVR models to improve the generalization capacity of T-SVR alone. The T-SVR algorithm learns ith random T-SVR model from ith bootstrap sample, sampling with replacement from the original dataset. For each non-terminal node in the training spaces of the tree regressor, randomly choose n apostrophe dimensions from n original ones are used to calculate the best list among the n apostrophe dimensions. We mentioned about the performance analysis of KR-SVR and RT-SVR. Parallel training algorithm for T random K-local SVR models on V-core computer. The complexity is OTM square divided KB. So, ensemble-based learning algorithm RK-SVR, RT-SVR, KR-SVR, RT-SVR are T times slower than single one KSVR and TSVR, respectively, but making the improvement of the generalization capacity. The ensemble-based learning algorithm is to yield a randomization of the learning sample for reducing variance and bias. Bias is the systematic error and not depending on the learning sample. Variance is the error with respect to the variability of the learning model due to the learning sample randomness. So ensemble random KSVR and TSVR can improve the generalization capacity. To evaluate the performance of our algorithm, we have implemented implemented it in C and C++ and used the standard library SVM using a PC Linux with Intel Core 4-core 3.2 GHz and 32 GB RAM. For description of the dataset, we use file dataset from UCI repository in our experiments. The table presents the description of data. We have 5 datasets, and the evaluation protocols are illustrated in the last column. Dataset already divided in training set and test set. In training set and test set, we use the training data to build SVR models. Then we predicted the test set using the resulting model. Dataset ID1 is the appliances energy prediction. Dataset ID2 is the Facebook comment volume. Dataset ID3 blog feedback. And boost in social media is ID4. The last one is year prediction MLSD. The hyperparameters are tuned for each dataset in the table. And KRSVR, RTSVR, Trend 10 KSVR, TSVR models. T is 10 and N apostrophe is square root of N used in KRSVR and RTSVR. We have here training time of regression algorithm and regression results in terms of mean absolute error. The training time of algorithm on 3 small datasets are visualized in this plot. And the training time of algorithm on 2 large datasets are shown in this plot chart. The prediction error in terms of mean absolute error are present in this chart. Our local SVR algorithms are more accurate than LibSVM. KRSVR will LibSVM 5 datasets. RTSVR will LibSVM 4/5 datasets. Comment on training time. The KSVR is more than 21 times faster than LibSVR. TSVR is 346 more times faster than LibSVR. KSVR is 3.97 times faster than LibSVR. RTSVR is 127.64 times faster than LibSVR. The comparison on training time on two small data sets show that KSVR is more than 200 times faster than LibSVR. GSVR is more than 2,000 times faster than LibSVR. KRSVR is 48 times faster than LibSVR. RGSVR is 34 times faster than LibSVR. For the average of training time, speed improvement of KSVR versus LibSVR 183 times. Speed improvement of GSVR versus LibSVR. Speed. So, training algorithm for local support vector regression models are significantly faster than the LibSVR. For the training time, KSVR is 4 times faster than KSVR. KRSVR. GSVR is 2 times faster than RGSVR. Example of local support prediction rule results prediction improvement of KRSVR versus KSVR is 0.98. Prediction improvement of RGSVR versus TSVR is 2.65. So, in example of local support vector regression, more accurate than single one of local support vector regression. Let's see about the conclusions. We have presented new local support vector regression algorithm for dealing with large dataset called KSVR, TSVR, KRSVR, and RGSVR. Training algorithm perform the regression task via two main steps: partition the large dataset into K subset. Local SVR model is learned from each subset. Parallel training local SVR model on multi-core computers. And theoretical analysis for performance, algorithmic complexity, generalization capacity. So the training algorithm for local support vector regression model are faster than the standard SVR while achieving the high generalization capacity. The numerical test results show that the training local SVR algorithms are faster than the standard SVR while achieving the high generalization capacity. Average of the training time algorithm for SVR, the model are significantly faster than LibSVR. The prediction correctness. Local SVR model are more accurate than LibSVR. So the proposed algorithm for local support vector regression models are efficient for handling large datasets. We can see the dataset number 5 year prediction MS. We have 400,000 individuals and 90 dimensions. So the TSVR perform in 3.2 minutes and with the mean absolute error is 7.38 on the test set. For algorithm KSVR, the training time is 6.3 minutes and mean absolute error on the test set is 7.86. KSVR more 700 and 300 times faster than libSVM. Prediction improvement obvious where KRSVR again libSVM is 0.8 and 0.3 medium mean absolute error on the test set. In the future, we intend to use another algorithm to split full training datasets, modify the prediction average rule, develop distributed algorithm for large-scale processing on an in-memory cluster computing platform, Apache Spark, and automatically tune hyperparameters. This is the publication. We have four papers published. We have two journal and paper and two conference paper. That's all from my presentation today. I would like to listen to your question and discuss. Thank you very much for your attention.